Okay, this is 2.6. We're going to talk about the graphs of rational functions. So you'll learn what a rational function is and how to transform it, limits and asymptotes. We'll analyze it, so we'll find the domain and range and all that good stuff. We'll use it to do some, we won't do relative humidity, but we'll do some other applications. All right, so let's look at an example then. Well, first of all, a rational function is just anything that's can be written as a fraction. So you have some function at the top, some function at the bottom. It can be x, on the top, and x squared minus 3 in the bottom, or something. There's some random function at the top, some in the bottom. It could be any function. It could be a square root function. Okay. Here's an example then. We want to use limits to describe the behavior of the values that are not in the domain. So the values not in the domain here, we know that we have an issue if we stick in -2. So we know that -2 would be actually a vertical asymptote according to our formula sheet, right? Because those occur at zeros at the bottom. So at x equals -2, we have a vertical asymptote. That's not in the domain. And so we can say our domain then is from -infinity all the way up to -2, but not including -2, and then -2 to positive infinity. And then it wants us to use limits to describe the behavior there. So we would graph this, 2 over x plus 2. Let me do that real quick. So you get this, and you can see that that value, -2, is an asymptote. It's not in our function. Now we can say as the limit approaches that from the left, it goes to -infinity, and as the limit approaches it from the right, it goes to positive infinity. So we would say it like this. We would say the limit of the function when x approaches -2 from the left went down to -infinity, and the limit as x approached -2 from the right went to positive infinity. So as x approaches -2 from the right goes to positive infinity, and as we approach -2 from the left goes to negative infinity. Okay, so that's what they mean when they say use limits to describe the behavior if that is not in the domain. All right, so here's what we would do when I ask you to analyze a function. So WebWorks going to ask you a bunch of questions. It's going to ask you sometimes for domain, range, x and y intercepts, things like that.
Jensen Peterson to A118.
So the domain of this function goes from -infinity all the way to 0, and then from 0 to positive infinity. We just can't include 0, so we have to kind of leave that out. The range, same thing. -infinity all the way up to 0, 0 to infinity. It's continuous on all x values. It's decreasing always, so it decreases on basically the whole domain, right? -infinity to 0 and 0 to positive infinity. It's symmetric with respect to the origin, means you can rotate it 180 degrees and it'll land back on top of itself. It's unbounded. Horizontal asymptote is at x or y equals 0, and vertical asymptote is at x equals 0. And then the end behavior, as the function goes to -infinity, this thing goes to 0, and as it goes to positive infinity, it goes to 0. So we can basically give all these properties. It doesn't have any x and y intercepts. Otherwise, we'd give those as well. All right. We're not going to deal with transforming these for now. We've already done that section. But let me do a couple more examples regarding things that you might be asked. So end behavior asymptote, I'll go over that in a second. First, let's find just like asymptotes. Now, horizontal asymptotes is on your formula sheet, and vertical asymptotes is as well. Vertical asymptotes occur as zeros at the bottom, so that'd be x equals -1 and -5. Okay, that's right in your formula sheet. Let me pull that up for you. So that's right here. It gives you all the information you need. Okay, now horizontal asymptotes, we actually have the same exponent in the numerator and the denominator for this problem, because if you FOIL this out and put it in standard form, you'd end up with 2x squared for your first term, and this one you'd end up with x squared at the bottom. So the formula sheet tells us that we want the ratio of the leading coefficients when the exponent's the same. So that'd be y equals 2 for our horizontal asymptote. All right. So we're going to use these different things that are on here. Sometimes if the exponent's higher in the bottom, then the asymptote's y equals 0. If the exponent's higher at the top, then there is no asymptote, and we're going to have an end behavior asymptote. Let me actually go over one of those examples real quick, because those are some of the trickier ones, I guess. You have x squared plus 2x minus 3, for example, over x plus 2. Now, if I asked you to find the asymptotes for this function, then we know the exponent's higher at the top and the bottom, so we have to do the long division. So we'll divide it in to this function. So the question is, what do I put up here to multiply by x to get x squared? That'd be x. Follow through. Subtract, that gives you 0. And then the remainder then is negative 3. So I'm going to write plus negative 3 over x plus 2, because we always put the remainder over the divisor. So basically what that means is this function, if I do the division, gives me this function. They're the equivalent functions, just represented in different ways. It's kind of like having like 17 over 3, which is really the same thing as 3 goes into 17 5 times with a remainder of 2. So these are like the same thing, right? We have a mixed fraction and a proper fraction. Same thing here. But the nice thing is about doing this is then we can see that, okay, what happens when x gets really big? We can look at end behavior. When x gets really, really big, this bottom gets big, which means this thing goes to 0. So basically, we know that eventually this function right here is going to become the function x. And I'll show you that in Desmos real quick. So you can see how this function eventually becomes the line y equals x. In fact, I'll graph the line y equals x and show you that it approaches that line. If we scroll out, you can see it. Eventually it becomes exactly that line, pretty much. Right. So that's called an end behavior asymptote, and that happens whenever the exponent's higher in the top than the bottom. And to find it, you just do the long division and throw away the remainder, and what you have left over is the end behavior asymptote. Okay, just do the long division and throw away the remainder. One last example then, this time the exponent's higher in the bottom than the top, so we have horizontal asymptotes and vertical asymptotes. Horizontal asymptotes would be y equals 0 whenever the exponent's higher in the bottom than the top. That's right in the formula sheet. Vertical asymptotes occur at 2 and negative 3. Those are places where the denominator is 0. And then want the intercepts as well, so x-intercept occurs where y is 0. So plug in 0 for y, and that'd be 1. And then the y-intercepts occur where x is 0, so plug in 0 for x, and you get negative 1 over negative 2 times 3, which is negative 1 over negative 6, which is 1/6. Okay? All right, we'll try a bunch more examples and talk more in the homework.